Hi, good evening. I thought tonight, rather than sit here doing nothing for the first 5 minutes, I would just sort of talk aimlessly, drink a cup of tea, draw on some bits of paper. People were absolutely fascinated yesterday that when I am at home, I'm not necessarily dressed in the same things that I would use for school. So I am wearing my own clothes. Apparently it's a big thing that I'm wearing my own clothes rather than someone else's clothes. And yeah, rather than just sit here in silence, gently waving at the camera, I mean, I can do that if you prefer. I thought I'd talk and at least fill the opening 5 minutes so it doesn't look like I'm just staring into a mirror for the whole thing. So there's a couple of you here now, so I'll get started. If you have any questions, just shout up in the chat on the side and I'll do my best to answer those as we go along. Try and keep them sensible. I'm going to do about 28, 29 minutes. We'll go as long as we need to. I've got some stuff, but I'm more than happy to field any questions that will help you through your exam tomorrow. Okay, so I thought we could start with some of the space stuff. We didn't do any space last night, so I thought we could talk a little bit about the solar system. We could talk a little bit about the universe, and then I'll spend a couple of minutes talking about some of the wider stuff for triple science students. Those guys have a little bit of extra to do on their course, so we'll spend a little bit of time talking about those. Okay, I think I might take my glasses off as well because I hate the flashback from the camera. Okay, so with the solar system, the important thing to remember are the orders of the planets. Roughly in order will help you out with some of the questions that they might throw at you. So you've got Mercury, Venus, Earth, Mars, Jupiter, Uranus, and Neptune. Okay, so there are however many of those there are. And we now have Pluto on the end, which is a dwarf planet. Rather than having this ninth planet as Pluto, we only have the 8. And it's too small. Basically, Pluto is too small. It's actually smaller than some of the moons in the rest of the solar system. We've got some other dwarf planets as well. So you might hear Eros mentioned, Ceres. There are a couple of others as well. And they're in places like the asteroid belt or in the Kuiper belt. Mentioning the asteroid belt, it's an interesting space in between Mars and Jupiter. Hi. So in between Mars and Jupiter, you've got an asteroid belt. There should really be another planet there, but it's never formed. Every time Jupiter and Mars go past each other, they they just disturb the stuff. So planets form. Yeah, no problem, Owen. So planets form by gathering together small things, a bit like if you were going for a walk, you might put together some friends to go with you. Planets form from lumps sticking together, and for some reason one hasn't formed, and we think it's the disturbance of Mars and Jupiter going past. So keep an eye out within the exam for maybe some texts to do with the formation of planets, that sort of thing. All of the planets formed out of a cloud of dust and gas called the planetary nebula. It was left over when the sun formed, so the sun itself formed out of a nebula. This takes me nicely on. It's almost like I planned this. This diagram, you should know this. This is a good thing to learn. If you want to learn a couple of things last minute, memorizing this diagram would be a good one. Okay, you can find it in lots of places. Just Google life cycle of a star, and it'll take you through this particular diagram. So I mentioned, didn't I, that the sun formed out of a nebula. So nebulas are huge. They can be a couple of light years across. So even as light, it'd take a whole year to travel across the size of some of these things. They're massive. So nebulas, big clouds of dust and gas, mainly hydrogen, tiny amounts of water, trace amounts of heavier elements from leftovers from other stars. And the nebula pulls together. Gravity is a big grouping force, and it pulls together all of the particles in the nebula until they start to get hot. As they crash into each other, they rub together, that sort of friction that you're aware of. Something similar to that causes a hot center, something we call a protostar. And we can see out there, if we use things like the Hubble Space Telescope, we can look out and we can see protostars just faintly glowing. And eventually we end up in the main sequence. So a protostar kicks off into the main sequence. And the main sequence is where we have our nice, stable, well-balanced stars. Here, the inward pull of gravity is balanced by the outward pressure of the light coming out. So the reaction in the center of a star inflates it, a bit like blowing up a balloon, and the gravity pulls it inwards, and those two reach a nice balance point, and the stars get very stable and nice, comfortable, nice things to live around. Our sun is currently in the main sequence. So this, the forces are nice and balanced. It's very stable. It doesn't do crazy things too often, and that makes it good for a good place to live. Now you've got two choices. Low mass stars, things that are small, come down this route. So when the main sequence star runs out of fuel, it can't support itself anymore, and it sort of collapses very quickly, and then it sort of balloons outwards because a different reaction happens at its center. So it grows basically into a red giant, which is cooler but bigger than the main sequence that it came from. And then it runs out of fuel again and becomes a white dwarf. Now, white dwarfs are incredibly hot, but really, really small. They're the leftover center of the star. But it's not sustainable. They can't stay as white dwarfs for very long because there's nothing to sustain the temperature of them. There's nothing to keep them warm. So eventually they fade and they cool and they fade and they become brown dwarfs. You might see an X-ray layer, you might see a black dwarf down here. Eventually they'll just fade and drop to the temperature of empty space. More interesting, sorry, our sun will come down this route because our sun is a low mass star, so it's coming down this side. That's one of our favorite questions, is to tell you or to ask you what the sun will do, or to tell you that a star is like the sun and ask you what will happen. Now, if we swap to the other side, so a high mass star, when it runs out of fuel in the main sequence, because it's really big, it goes supergiant. That's how you're going to remember. Supersized milkshake, supersized star, supergiant. And these things are a bit cooler, but they're often absolutely huge. We can see one with your eye in the back garden on a dark night. You can see Betelgeuse. Betelgeuse is 200 times bigger than the whole solar system. It's massive. And this guy, when he runs out of fuel, he doesn't sort of gently fade into, sorry, he doesn't sort of turn into a white dwarf. There's a really violent, huge explosion called a supernova. And that's very important for life on Earth because lots of the complicated elements, the big elements that we need for life are formed in the supernova stage, in that giant explosion. And when the supernova happens, these things will take days, a week at the most. That doesn't seem really fast, but when you're a star that lives 5 billion, 6 billion years, that's pretty quick. Leaves behind either a black hole or a neutron star, and at GCSE, who even cares what the difference between those two things are? Okay, these guys are super dense. They're so dense that light is trapped by them. They can't light can't get out. It's very difficult to find anything out about these at all. You may have recently seen in the news that we've just imaged the spiraling dust around the outside of a black hole. So we can't see them, but we can see what's going on around them. They're very weird, very interesting objects. You should read some Stephen Hawking about that, but only after you finish your exams. So questions you're likely to get on space, probably, thanks Aaron, probably something to do with the life cycle of the stars. They quite like things like, where did our solar system come from? And that's where you're going to talk about the idea of this nebula collapsing to form the sun, and then the planetary nebula, the leftover gas and dust from that process clumping together to make larger planets and smaller planets, rocky and gassy planets, depending what's left over in the mix. Okay, so I'm just going to take a second. If you're not a triple award student, I know I've got a couple of you guys with me today. If you're not a triple award student, you can look away now, and now's a good time to go for a wee. You guys in the triple, you need to know a little bit more here. So you need to know that we have this thing called redshift, and redshift is evidence that all of the galaxies in the sky are moving away from us. So if we look at the light from a star, so if we take this top one, for example, we should have a nice pretty rainbow that goes from blue to red or red to blue. And the elements in the sun, so sodium, helium, hydrogen, they will take colors. They will leave little black lines in the rainbow. So this spectrum will be missing something. This is called an absorption spectrum. And if we look at the absorption spectra for galaxies, we see this. We see that these lines, they match perfectly, except they've been shifted towards the red, and that's where the phrase red shift comes from. So these guys here get pushed off towards the red. And that's interesting because we can do a bit of clever maths, we can do some nice physics to this, and we can calculate how fast this galaxy is moving away if this is our standard one. So we can work it out. And that interesting evidence that comes from that is that the further away a galaxy is, the faster it's moving. So we can quite quickly measure how quickly space is expanding. We can track it back. We can find out things like the age of the universe and stuff. It's an interesting piece of groundbreaking 20th century science, this. There's something else that comes with it, and that's the cosmic microwave background. So if there was a Big Bang at the beginning of the universe, the universe should still basically be cooling down from that giant explosion. We should be able to look out into space, and we should be able to see the energy. We should be able to see the bang, basically, from the Big Bang. It's not light anymore. It's not X-rays. It's the universe has stretched. So if you visualize waves like a slinky on a like the what do you call them? The spring, a slinky spring. If the universe gets bigger, the spring gets stretched. So as the spring gets stretched, all of the little loops in between it get a little bit further apart. So that's a bit like the peaks and troughs on a wave. So they get pulled a little bit further apart. And that means that now, instead of being gamma rays, instead of being high energy radiation in a small environment, everything has been pulled a bit wider apart. So now the bang is basically microwaves now. And when we look out, we can do this using special radio telescopes. We can measure microwave background. And everywhere we look in the universe, we see cosmic microwave background. It's the only explanation for cosmic microwave background is the Big Bang. So it's essentially evidence. It's almost conclusive evidence that something, the Big Bang happened. Okay, so that's the life cycle of stars and the wider universe stuff for the triple scientist among you. Okay, so I thought this is one of my favorites. This quite often comes up very early on in the exam, so we'll have a quick look at this because it's a nice way to get started. What maths is needed to find out the age of a planet using a spectrum? We can't age a planet from a spectrum, Ben, but what we could do is we could measure the elements present. So this absorption spectrum, if I look very closely at an absorption spectrum, I can work out what caused it. So I can spot oxygen, I can spot hydrogen, I can even go closer to that. I can actually see molecules, so more complicated molecules like methane. Methane is a telltale indicator of life because it comes from rotting organic materials. So cows give off a lot of methane when they're digesting grass. So if I look at the spectrum of light coming from a planet, maybe an extrasolar planet, so a planet millions of light years away, as long as I've got the detail on my telescope and I can see this spectrum, I can work out if it has an atmosphere, and if it has an atmosphere, what's in that atmosphere. And it might be that I can detect the signs of life on the other side of the universe, even though I've never been, just from looking basically at the lines missing in the absorption spectrum. Is that what you meant? Lovely bit of silence there. Yes, brilliant. Okay, so just a general tip here for your exams, particularly in the sciences where you have lots of questions on lots of different topic areas. It feels really bad, doesn't it, when you open an exam paper and the first question is something you don't know, and you look at it and you think, oh my God, I can't do any of this. It's just going to be a nightmare. So go to question 2, and then go to question 3, and then go to question 4. Work your way from front to back through the exam paper, doing the questions you can do, because then you've started positively, you've scored some marks, and you're off and you're going. And then go back and start filling in. Then start, when your confidence is up a little bit, start using your guesswork, start puzzling it out, solving those problems. The more complicated, the not so obvious first off. Do what you can first, and then move on, or then move back through the exam paper, filling in the stuff that you can't. Try really hard not to leave any question unanswered, even if you think, oh, that's a bit of a daft guess. It is better to write something than to write nothing at all. You get no marks for nothing every time. Right, talking about nice and easy to score some marks. Distance time graphs, one of my favorites. I did these at length yesterday, but I'm just going to run through very quickly what's going on here. So if this is my distance axis, and this is my moving further away from the start, and then it stops for a bit, and then it moves further away again. Now, can you see how this line is not very steep, but this line is really steep over here? The slope of this line is how fast it's traveling. So this one is not going particularly quickly. Obviously, there's no slope, so no speed, and then a really steep slope, so this must be a really high speed here. Okay, so watch out for little things like that. So that's a distance time graph. And the distance time graph has a friend. It's the velocity time graph. I can't work out where to hold it though. So the velocity time graph, again, velocity on the y-axis up here, and then time down here. This tells us a little bit more. So I can see that this object is moving away from the origin, so moving away from where it started, up. And then here, it does something interesting. Lots of us might be tricked because it's flat into saying that it stopped moving. But that's not quite what's happened. It's just moving at a constant speed. And then it's actually moving, it's slowing down, I should say, to 0 here. Okay, so it's not gone backwards. This is not backwards. That would be on a distance time. It has accelerated, reached a constant maximum speed, and then it's decelerated back to 0 again. So it's now stopped here at the bottom. I can do two things from this graph. I can find the slope here. I can find out how steep this line is. If this line is really steep, that tells me that it is going to be moving really quickly. If it's moving, obviously, here, they've got a negative slope. That's going to tell me that it's slowing down, right? So we're measuring acceleration from the slope of this graph. I could find the area underneath. Now, I can't because I've got no numbers, but the exam guys will give you some numbers on these axes. They might ask you to chop it up into two triangles at either end and a rectangle in the middle. And you can do that to then work out the total area, and that is the distance traveled. It's basically speed times time, which gives you distance traveled. Remember, on page 2, there's some useful hints. The equations are there. You don't need to remember those equations. You do have to recognize them, though. So if you're unsure, have a bit of a look at one of those. Come and find me tomorrow morning, and I can show you page 2 of a formula booklet. So and just remind you what each of those are for. You get formulae with symbols. You also get words as well. So don't be put off. Don't try and fill in any of those blanks. That's like a help sheet for you. A bit like in your chemistry, you get some information at the back of your exam paper. Okay, so I've now got, we'll do some very quick radiation. Did some radiation yesterday, so I've got that in blue. Just to recap what we did, we talked about an alpha particle is a helium nucleus, and that's got total four nucleons, can't say it, 4 nucleons, so that's 2 protons and 2 neutrons. It's got 2 for its atomic number or its proton number, so 4, 2, He. This is a helium nucleus. This is an alpha particle, and they are highly ionizing but have very short range. This is my beta particle. My beta particle is 0 because it's got no mass. I mean, I'll get away with that. I don't think Aaron's watching anymore. So it's got no mass, and -1 for a proton number. That's because it's not a proton and it's got a -1 charge. We'll just pretend it's not happening. But -1 down here. Oh, here he is. Okay, so we've got a negative charge in this. It's a fast electron. So 0, -1, fast electron, beta particle. Okay, and then lastly, I've got my gamma particle down here at the end. This guy has got no mass and he's got no proton number. It's pure energy. It's just a wave. Okay, these are the easiest things to solve if you get one. So they're not going to give you one. Okay, because nothing changes. So highly ionizing, low penetrating, sort of in the middle. The beta particle, really, really penetrating, travels miles and miles and miles and miles. Some of the gamma rays are hitting you from the other side of the universe right now, going straight through your body, but very weakly ionizing, so not as damaging relative to a helium. So if you were going, relative to an alpha. So if you got hit by 1 alpha or 1 gamma, the alpha will do more damage. The gamma is likely, to be honest, to pass straight through you. Okay. So where do you need to use those? We can use those in this sort of equation here. So this is the alpha decay. Spot the alpha particle down here at the end. This is the alpha decay of uranium-238. Now, 238, that's the mass number. Uranium is an interesting element. It has lots of different isotopes. An isotope has a different mass number, so this number up here can change, but will always have the same number of protons. The 92 is what makes it uranium. So this uranium has spat out an alpha particle over here. And as it spat that alpha particle out, it changed. So 4 of this 238 are over here now. So there's only 234 left. And we started with 92, 2 of them are over here, so we've got 90 here. Now I've looked up in advance that this is thorium. You might be given some, all, or none of this. Different questions, different standard will ask you to do different things. The most likely situation is they will maybe cover up 1 or 2 of the numbers and then ask you to fill in the missing bits. So watch out for them doing that. Keep an eye out, remember, on your exam paper for places that it looks like you should write. Everywhere it says there's a mark, there should be something to do. So keep an eye out for that for me. Excuse me. Okay, right. So if that's alpha, this one's beta. Now you can see I made a mistake. You know, terrible. Happens to the best of us. So beta decay. So this is a 14 carbon, so carbon 14, another isotope of carbon. Carbon comes in several isotopes. Carbon 12 is the most common. Carbon 14 is also pretty common. And this guy, C14, he's not stable. Just like the uranium, it's not stable, and it wants to change in order to... I don't know, Ben. A higher tier triple paper will quite possibly ask you to fill in 1 or 2 of the blanks, if I'm honest. It's not a very difficult skill, so it's not worth giving you a 4-mark question on, because if you give 4 marks, then you'll need 5 minutes to answer it. So it's not worth spending that much time on for the exam. So they will likely just give you 1 or 2 missing values from in the equation. So my carbon is unstable, and that means it wants to decay. This time we're going to get a beta decay, so that's 0 minus 1. So if I start with 6 and I've got 7 here, then this one, oh sorry, I've got -1 here. This one must be 7 here in the middle, okay? If I start with 14 and I've got none up here, then I must still have 14 here. So this carbon has become a nitrogen. Again, I've looked that up. So you just solve it. You just need to balance. A bit like chemistry, if you were solving the number of moles or looking at the different layouts within formulae, you just do the same. It has to balance across. There's no equal sign. You just balance it across the arrow like you would in chemistry. Okay. So we can talk half-life while we're here as well. Half-life is the amount of time it takes for the activity of a sample to drop by half. Okay, I'm just really quickly drawing you something here. Okay, so can't draw and talk, it turns out. So this is a half-life curve. So we've got activity up on this axis, and we've got time down here on this axis. And what's happening here is, because some of the atoms have gone, there is less to decay as we go along. So it decreases. This is called an exponential decrease. And you won't have to do much with it other than perhaps measure the half-life. So what you do is you look at what the value is up there at the top, and you have to go halfway. I'll try and do this. There. And then you draw down. Oh, like that, okay? Use a ruler, top tip, okay? So we've got across and then down. And if you read off this here, that will tell you the half-life of the thing. Now, Owen's asking me about the second half-life. I'm just going to tidy my graph up because, quite frankly, it's giving me the creeps. So if I draw this, so you can see here how I've done it again. So I've gone halfway down again from here down to the bottom. So halfway down, go across. And can you see, even on my really badly drawn graph, that this distance here, so this first half-life, and this next measurement of half-life, they're roughly the same, aren't they? And if your graph is drawn well enough and you've done a better job than I have, you'll find that every time it halves as you go across, the amount of time it takes to go down by half stays the same every time. Sometimes, Owen, they will ask you to find the second half to prove that the first half is correct. Or maybe if they've given you some experimental data, maybe they'll then ask you to take a mean or something. So yes, it's good that you're aware we can find a second half-life. It's unlikely, but it is possible that they will ask you to do that, okay? Very quickly, if it's got a low half-life, if it's got a short half-life, it will have a very high activity. If it's got a long half-life, we're all really scared about stuff with like 5 billion year half-life, but no, because long half-life, low activity. If you get a question about radioactive tracers, remember, a radioactive tracer is something that we can put inside your body. We can either feed it to you, or we can inject it, or we can actually, you can inhale it. And then we can stand you in front of a detector and we can detect maybe where the gamma radiation is coming from that radioactive material. We would choose something that had a short-ish half-life, something maybe with a half-life of a few hours, so that you can, so that you're not, or that radiation isn't lingering in your system for a long time. So technetium is a wonderful one for that. They might ask you to choose between two isotopes to decide which one is the best to use. Yes, Ben, if we measure the second half-life, it should be the same as the first one. In fact, all the way, every time, it's a mathematical relationship. It should always be the same. So we want to choose the right half-life. The right half-life is the one that's long enough to allow you to do your job, but not so long it's going to kick around for ages, but also not so short it's going to give you a huge dose of radiation. Okay. Read the question. Big tip as well. They will be bombarding you with information throughout the whole exam. Some of it you won't need. Some of it you will have to have a bit of think about and decide whether or not it's useful within the question or not. Okay. Can't remember what I was going to do next. Lost my little bits of paper. Owen's asked me to do something on gravitational potential energy and things. So you've got two key equations here, and they are given to you on the exam paper. Just going to write them down so we can see them. Okay, so the first one I'll talk about is gravitational potential. So if I lift an object up off the floor, I have to do work. There's a force called weight pulling things down towards the floor. And in order to overcome the weight, I have to put a force of my own in. If I apply a force over a distance, I'm lifting an object and I'm filling a gravitational potential store. So an object, tennis ball, football, lifted off the ground will have gravitational energy. So it's the dog trying to get into the dining room. So as I lift the ball up, gains gravitational potential energy. How much? Well, that's what I want to know. I mean, seriously, it actually is what I want to know. So I take the mass of the tennis ball, and I times it by the gravitational field strength or acceleration due to gravity. And I times it by the height through which I've lifted it. Okay, and that will give me a value in joules. With G, they will tell you in the question, but just in case you want to speed life up for yourself, on Earth, G is always 10. So you'll have a mass times by 10 times by height. Nice and easy. Chuck it all in your calculator and times it all out. Answer out in joules. And then, last bit, these bits quite often come together. So this is kinetic energy here. So kinetic energy, that's movement energy. So if I was to take that ball, lift it all the way up, got gravitational, and let go of it, the gravitational potential will transfer into kinetic energy as it falls. Now, as that ball hits the floor, the very instant, imagine that you could barely slide a piece of paper in between the ball and the desk, and you just freeze time for a minute, and you want to know the energy that that falling ball will have. It will have exactly the same energy as the gravitational store at the top. So the start at the top and the finish at the bottom will have the same amount of energy in both. It's one of the rules of the universe. And how much? How much? Tell me how much. Well, for that, we need to do another bit of maths. So it's the big important thing is this. I don't know if that looks like an M to you. It looks like an M to me, I suppose. You take the mass and times it by velocity squared. Now, it's important you do that bit first. Velocity, remember, is a posh word for speed. It means speed in a particular direction. So you do that squared times by the mass, and then this bit. This bit puts so many of you off, and don't let it put you off. It's just a half. So you can either do this bit first and then divide it by 2, or you can put 0.5 in your calculator, or you can put a half in. If you've got a clever calculator like this, you can put a half into that. And times the whole lot through together. It's important, though, that you square velocity and don't accidentally square all of this. So maybe, if you want my advice, start on the right and work backwards across until you get to the answer. Okay. There is one last equation I'll talk about on this one, and it goes back to something I said a moment ago, which is that so it was this one. I said when I lifted the ball upwards, thanks, Dylan. When I lift the ball upwards, I'm doing work. and work is equal to the force that I have to lift it with times the distance by which I lifted it. Okay, so watch out for that as well. We sometimes get questions about lift motors pulling like objects up a hill. We get all sorts of stuff like that. We get cranes lifting boxes and stuff. And you're asked to talk about like the work done and the gravitational potential energy gained and things like that. Just watch out. Sometimes I like to throw this one right in at the end of a question. They might say that when it was actually measured, they measured the gravitational potential, they measured the kinetic, and this was found not to be as much as you've just worked out in the question. So I don't know, part A is calculate this, part B is calculate this, part C, why aren't the two the same? In the real world, things get messed up in physics. So air resistance transfers energy from the gravitational store, from the kinetic store. It steals a bit of that away as air through air resistance, and it makes it warm. So as objects move through the air, they leave behind them warmer air. And that means that the two numbers don't quite add up sometimes, okay? But that'll be right at the end of the question once you've done all of your maths, okay? Okay, so there's 31 minutes of me rabbiting on, waffling along. Can I help anyone with any specific questions that they have? Or shall we call it there? Shall I leave it there for the evening? I'm just going to have a cup of tea while you guys sort yourselves out. You're welcome, Dylan. It's no problem at all. I'm glad you enjoyed the calculator as well. It was a gift from some Year 11s last year, so I'm obviously not that hated as I was last time. Celebrity spotting. She's just gone straight past the door. Yes, Owen, I'll do some revision. You can. I've got Year 11s period 1 and 2. So depending on what you've got, period 1 and 2 tomorrow, if there's any arrangement that can be made, you're welcome to pop out. Flynn, I'll be in school from probably about 10 to 8. So you're welcome to come and find me then if you want. But you're welcome as well, because it's an afternoon exam. You're welcome to come up at lunchtime. I'll make sure I've got some sandwiches or something, and we can sit and do lunch together, and you can ask any specific questions, and I'll go through anything that you've got a problem with. Same true at break time. Just come and find me, to be honest. Okay, I wonder what she's getting from the cupboard. Hopefully something tasty. Sorry, Dylan, I can't send you the calculator via email. It's just too much. You're very welcome, guys. Remember, if you've enjoyed yourself today, tell your friends. There'll be a recording. It'll be saved up online, so you'll be able to get it through the Boring Physics video channel. If you want to leave any comments or ask any questions for me, and I'll try and answer them tomorrow. Remember, there's loads of other videos showing you how to do different exam questions. I think there's like 5 or 6 now. Yeah, bring me any questions. Give me some thumbs up and stuff like that. It makes me feel like I've not just been talking to a mirror all by myself for the last hour. Marin, you're a whole year too early, I'm afraid. You're very welcome, guys. Yeah, absolutely welcome. Okay, I'm going to say good night. Don't stress out. Get a good night's sleep tonight, and I'll see some of you tomorrow morning. And, well, I'll see about 30 of you, I hope, tomorrow morning. And take it easy. Thanks. Bye.